Induced EMF and magnetic flux. In the electric circuit chapter, we talked about electromotive force. It is actually a potential difference between 2 points that is measured in volts. It is not a force, but it's a historical term that has just not gone away. Because of its unfortunate name, it is frequently just referred to as EMF or this script-looking E here. It represented the maximum possible voltage from a battery during the electric current section before it was reduced by the battery's internal resistance, and then if you'll recall, that was called terminal voltage. This chapter is going to show a way that a voltage can be developed in a conducting wire that is not connected to a battery. Ørsted and Ampere both showed that a current will generate a magnetic field. If you're a physicist, what's the next thing you want to check up? Of course, you want to see if the reverse can be true. Can a magnetic field generate a current? Michael Faraday, we've talked about him before, was able to make this connection in 1831. However, the magnetic field had to change, either in magnitude or orientation to the wire where the current was being created. Don't worry about that yet. We'll show pictures and go into more detail. The interesting part, in America at the same time, Joseph Henry discovered this phenomenon, but he didn't publish it. Faraday published it first, so he gets credit for it. But don't feel bad for Henry. They named the unit of inductance Henry in his honor. This happens a lot in mathematics and physics. For example, in calculus, Newton in the UK developed it, and Leibniz in Germany developed a very related form, both at the same time, independent of each other. And depending on what country you're in, that's who they claim created calculus. UK, you would say it would be Newton, and in Germany, Leibniz. Here's a schematic of the experimental setup that Michael Faraday used. He connected a battery, here's your battery, to a metal coil via insulated wires. And the whole point of this coil is just to magnify the magnetic field. It increases the magnetic field due to the magnetic field generated by these wires, by the current in these wires. Now let's look at this. Never is there any current in this metal coil. That's what this comment is. Never any current there, just the magnetic field. These wires are insulated. No current passes through them to the coil. So when I close this circuit, current will go like this through the wires, never going into the coil, and then back to the other end of the battery. If the current is steady, so if you've had this battery hooked up for a real long time, there's absolutely no voltage or current developed over here. And what do we have on this side? We have a wire wrapped around, comes back, and this is a voltmeter. So the voltmeter reads 0 when the switch is open, and it would also read 0 after the switch was closed for a long time. However, what Faraday and Henry also found, when you close the switch, you will get a current, and then later when you open it, you'll get a current. That's kind of wild. When the switch was closed, see here the switch is closed here to that red line. The ammeter, this guy here, in the secondary loop, that's what we're going to call this loop here that doesn't have the battery, gave a positive reading, indicating a counterclockwise current flow. However, after the switch had been closed a short time, the ammeter went back to 0. There was no current flowing in the secondary loop, but you still had current flowing in the primary loop. It's only when the current changed did you get an ammeter reading. When the switch was then opened again after it had been closed, see, it's open like this, the ammeter in the secondary loop gave a negative reading, indicating a clockwise current flow in the secondary loop. After the switch had been open a short time, the ammeter went back to 0. There was no current flowing at all here. What was cool here is you had current flowing in the secondary loop, although there was no current in the loop with the battery. Something was induced over here. We'll show 2 more examples of where a voltage and a current were induced without a battery. This is Faraday's disc generator. It looks like something you'd slice bologna with in a deli. You have a metal disc here, and you have a little handle here that you can spin it. Here you have a magnet, a horseshoe magnet, and what happens is as you spin this metal wheel, the points on the wheel will see a changing magnetic field. Here you'll have a strong magnetic field, then as you go far away from it, the magnetic field gets weaker and weaker. Therefore, since this magnetic field is changing, a current will be induced that is picked off the disc here by this little brush here. Here's one connection, and here's the other connection. And you can have a current that you can take off to an ammeter and measure. A bar magnet over here that moves towards, through, or away from a loop of wire will generate an EMF and then a current in the loop. A current will flow in here just because you're moving the battery. A current will also be generated if the magnet stays constant, doesn't move, and then you spin this loop around an axis like this. So you're kind of spinning it out of the page. You will find an induced EMF and a current. If you just hold the magnet there and the loop isn't moving, no current is generated in the loop. It's now time to explain what's going on. We now have evidence that a magnetic field can generate a current. But there is a difference between this and a current generating a magnetic field. A steady current will generate a magnetic field. We did that in the last unit. However, a steady magnetic field and a non-moving constant area loop of wire will not result in a current in the wire. However, a constant magnetic field and a moving loop of wire will result in a current. A changing magnetic field and a stationary loop of wire will result in a current. A constant magnetic field and a changing area of the loop of wire that the field goes through will result in a current. That's a lot for one paragraph, and we're going to go through that in some detail and make it a lot clearer. But first, we're going to have to define magnetic flux before we can fully understand what's going on. Magnetic flux describes the quantity of magnetic field lines that pass in a perpendicular direction through a given surface area and is represented by flux B equals B perpendicular times A. Phi is the Greek letter phi and stands for flux or flow. Adding the subscript B makes it magnetic flux. Electric flux, of course, would have a subscript of E. The unit of magnetic flux is the Weber, where 1 Weber equals 1 Tesla meter squared. And you can see that right here, right? Magnetic field is Tesla, area is square meter, so it's Tesla meter squared, and it's Weber. Again, named after a famous physicist. Another definition or reuse of something we've already seen in mechanics and electricity. We need the normal. The normal is a line that is perpendicular to a surface. So here's a surface kind of coming out of the board here. And you have a normal that is perpendicular. There's perpendicular to the top side of the surface. And here, coming underneath, is perpendicular to the underside. The magnetic flux would be at a maximum at any point on the surface where it is parallel to the normal. So it gets a little tricky here. I mean, right here is we kind of summarize it. Where your magnetic field lines are perpendicular to the surface, it's at a maximum. But when you're perpendicular to the surface, you are parallel to the normal. And normal is a very handy concept, and we'll use that more than we do surface. So we've defined magnetic flux and shown where it's a maximum and where it's a minimum. So let's get back to the guy whose name we took as units. Wilhelm Eduard Weber was a German professor and physicist who stressed the importance of experiments for students learning physics. He also worked and published with Carl Friedrich Gauss, and together they developed the first electromagnetic telegraph. However, he started getting into politics here, which is never a good idea for a physicist, and he lost one of his university teaching positions as he was doing politics against the King of Hanover. He should have stuck with physics. Here's our surface, this yellow surface here. Here's the normal lines, that one going up, that one coming down. And we have magnetic field lines. We have a magnetic field that is perpendicular to the plane of the loop of wire, this orange surface here, and parallel to the normal, the two normals. See how they're parallel here? Therefore, the magnetic flux is at a maximum and is equal to the strength of the magnetic field times the area of this loop. Again, here's our surface or loop of wire. The two normal lines are drawn, one below, one above, and we have a magnetic field that is parallel to the plane of the loop of wire, and it is perpendicular to the normal. So the magnetic flux is at a minimum, and this time the flux is zero. An easy way to look at that is if there are no magnetic field lines going through the plane of the loop of wire, then there's zero flux. It's a little tricky to see here, but they're just bypassing the plane. Nobody's going through the plane, so you have zero flux. The magnetic flux is proportional to the total number of magnetic field lines passing through a loop. Let's take three cases here. We've actually already done this case and this case, but we want to go intermediate. Here, the magnetic field is perpendicular to the normal. Here's the surface we're talking about here. Over here, the magnetic field lines are parallel to the normal, and you can see that the angle it makes is 0. We're measuring the angle to the normal. Here it's 90. We know that the flux is 0 in this case, and it's a max here. Here my angle between the normal and the field line, so let me just draw the field line right there. This angle here, you always measure to the normal. That theta is 45 degrees. And oh yeah, I even put that in red just to make sure you can see it. What happens here? What's the flux in this middle position? Here you have zero flux because no lines are passing through the disk. Okay, this actually is infinitely thin, so we're not going to count that line there going through. Over here, let's just count the lines that go through the surface. 1, 2, 3, 4, 5, 6. Let's call this 6.5. Because this is just a representation anyway. There's actually an infinite amount of field lines going through there. Let's count the field lines going here when we're at the 45 degree angle. 1, 2, 3, 4, and it depends how you count this guy. We'll call him 5 anyway, all right? This is just approximations. There are fewer lines going through here than this. So the flux, when you're at this angle, will be less than the maximum flux, but greater than the zero flux. Example 1. A wire loop with an area of 0.0050 square meters is oriented perpendicular to a uniform magnetic field of 1.30 Tesla. What is the magnetic flux through the loop? We write our givens right here. We have the area and also the magnetic field. Since the magnetic field is perpendicular to the loop of wire, the magnetic flux is a maximum through the loop. So we can just use this definition here. Flux is B times A. Substitute in the givens, and we get 6.5 times 10 to the minus 5th Webers. The magnetic flux through a rectangular loop with an area of 0.0080 square meters is 0.40 Webers. The magnetic field is perpendicular to the loop. How strong is the magnetic field? We write our givens right here. And then, since the magnetic field is perpendicular to the loop of wire, the magnetic flux is a maximum through the loop. So we can just use this equation here where flux is equal to BA perpendicular, and it is perpendicular, so we just need the value of B and the cross-sectional area. But we're trying to find B, so we divide both sides by A, and we have an expression for B. We substitute in our givens, and we get a magnetic field strength of 50 Tesla.